In this video, I want to look at an example of a derivative and then use that derivative to backwards engineer how to find a certain sort of indefinite integral. We will formalize the technique in the next video. So I want to get started with this basic derivative example. If I want to take the derivative of something like the sine of x cubed plus 5, I need the chain rule because this is a composition. I am looking at the sine of x cubed plus 5. And the chain rule says that to take the derivative of a composition, we need to take the derivative of the outside function, in this case that is sine, and the derivative of sine is cosine, but we evaluate that at the inside function, which is x cubed plus 5. And then we have to multiply by the derivative of the inside function. And so our final answer turns out to be 3x squared times the cosine of x cubed plus 5. Now what I want to do is I want to turn this particular problem around into an integration problem, finding an antiderivative. Suppose I want the antiderivative of x squared times the cosine of x cubed plus 5 dx. Now, I also want to state something over here. I kind of already know from the derivative thing, so from the example, I actually do know that my antiderivative is going to be sine of x cubed plus 5, and I'm going to have to divide by this particular 3 here to get everything to work out. In other words, if I have this function and I calculate f prime, that's going to be 1/3 times the previous derivative that we just calculated. And those 3's cancel out, and so f prime is indeed x squared times the cosine of x cubed plus 5. So I actually already know that the answer to this particular antiderivative should be this particular function plus whatever constant that I want to add. The question is how can I find this antiderivative if I don't have this particular derivative fact hanging around in front of me? And so I kind of want to think about how would I build this up without having the derivative in front of me. And so let's look at that particular problem. The first thing that I want to note in just looking at this particular integral problem is we have a composition here. So we have a composition. This is cosine of, I'm just going to call it stuff. And the second thing that I want to note is I also want to note that the derivative of the stuff is 3x squared, and there is an x squared. This is part of the d dx of the stuff. And I also know that constants can go back and forth through an integral sign. So if I also add to this integral a 3/3, I can pull this 3 in, and now I've got the derivative of the stuff. And this process is going to rewrite the derivative as 1/3 times the integral of the cosine of stuff. And then there's going to be a d stuff. We're going to have to formalize this in much more detail, but that will give me 1/3 of the sine of stuff. Let me see, I forgot to write down the sine. So the answer is going to give me 1/3 times the sine of the stuff. Now, obviously, I don't want to have to be writing all of this silly junk every single time I want to do one of these integrals. So what I really want to do is I want to come up with a systematic way of identifying I have a composition and I have enough of the derivative of the inside function to be able to patch the integral up and get it to work right. So let's look at a new panel with the exact same problem. So I want to be thinking about the integral of x squared times the cosine of x cubed plus 5 dx. Now, as before, I see that this is an inside function and that is an outside function. So what I'm going to do is I'm going to it's the traditional letter to use is u. So I'm going to let u be x cubed plus 5. And then I'm going to find the derivative of u with respect to x, and that is 3x squared. And then I need to convert this to differential notation, and that's basically, symbolically, it looks like we multiply by a dx, but I want to talk about what we're doing in just a minute. The symbolic conversion is du is equal to 3x squared times dx. I want to talk about this notational stuff in just a minute, but first I want to patch the integral up. I'm missing that 3, so I put a 3 out front and a 3 over 3 out front. I am going to bring the top 3 in and rewrite this integral as 1/3 times the integral of 3x squared times the cosine of x cubed plus 5 dx. And now it is a matter of realizing that these two chunks together form a du, and this itself is a u, so we can rewrite the integral as 1/3 times the cosine of u du, and the cosine of u du's antiderivative is going to be sine of u plus any constant, and then I want to back substitute u is equal to x cubed plus 5, and when we put that in, we get as a final answer 1/3 times the sine of x cubed plus 5 plus a constant. Now, the final things that I do want to say is a little bit of stuff about this notation. When we write du is equal to dx is equal to 3x squared, we are saying that the derivative of u is the function 3x squared. When we write du is equal to 3x squared times dx, we are saying that the change in the variable u is equal to 3x squared times the change in the variable x. And it's important that we want to be thinking about this differential notation, because that's what this is. This is called differential notation. And it's important to think about that because when we are looking at antiderivatives, the antiderivatives are written in terms of differential notation. So I want to think about what it means when we are actually writing an antiderivative with integral notation. So when we are writing the antiderivative of f of x dx, what we are saying is that we want an antiderivative with respect of the function f with respect to how x is changing. And this would be f of x. When we write the thing, so this dx in this kind of notation is representing the change in x. And so when we do this u-substitution, we have to do a change in x and convert it to a change in u. In the next video, we're going to formalize this technique that we just looked at.